Hello, everybody. Thanks for coming so early in the morning to come and watch my talk. Today I'm going to talk about packed arrays, and then I'm going to talk about a generalization of packed arrays that we've been working on called NumericArrays. Does everybody know what a packed array is? So a packed array, it started life in the old compiler as a data structure. It should be on, isn't it? Yeah. I'll reboot it. Yeah? Is that better? So packed arrays were added to the kernel. They started life inside the compiler when we added arrays of functions. And then they were added to the kernel as a genuine expression, a wrapper for the data structure. They have three basic types: a machine integer, that's the largest signed machine integer on the machine; a machine real, a 64-bit floating point number; or a machine complex, which is a pair of real 64-bit numbers. They match the native machine types in Mathematica. And the functionality was refined after the release over successive versions. So what's the difference? Packed arrays are practically indistinguishable from lists. Many functions generate packed arrays automatically. So here's an example. Here, this function range knows that it's working with machine numbers. It makes this thing here. And then I type in manually this list of numbers, and I get this thing here. This is a list. And this is actually a packed array, and you can use this special function to distinguish between the two. So a packed array essentially lays out all the data as a machine array consecutively, whereas a list has a Mathematica data structure wrapped around each number. Okay? So you can see here you have better data locality, but here you have more generality, because these things can live and they can mix with symbols, and they can mix with rational numbers and all the other types of expressions that we have in Mathematica. And another advantage is that packed arrays, because they use consecutive machine registers, they use less memory. Okay? So the disadvantages of a packed array, well, I put this down also as a disadvantage, that they're indistinguishable from lists. You often don't know if you're working with a packed array or not, and that can be a bit frustrating. It can be difficult to track when operations are packed and unpacked. Often we take a list, a Mathematica list, and we automatically pack it to a packed array, do some computation to make it more efficient, and then unpack it back to a list. And it's often difficult for a user to know when that sort of thing is going on. And the other thing is that in order for them to coexist seamlessly with the system, we switch in and out of packed arrays. So here's an example where I make a packed array containing the maximum machine number. Okay, this confirms it's a packed array. Then I multiply it by 2. An exception's generated. That number can no longer fit as a machine real number. And Mathematica switches to arbitrary precision to compute this result. Okay, so I've switched out of the realm of a machine array into the realm of a list. And all that stuff has gone on behind the scenes. So it makes for a good system integration, but it makes for a non-constant running time, because obviously this arbitrary precision computation is much, much slower than the machine precision computation. So what's a numeric array? A numeric array is a generalization of packed array. So we no longer have the restriction of using the largest machine precision types. We have 8, 16, 32, and 64-bit signed and unsigned integers. Real 32, which is a float, or real 64, which is a double, and the complex equivalents of those. So the obvious benefits are memory and speed, which is useful in the new compiler, audio-video processing, or machine learning. But this generalization to types brings with it its own set of issues that I'll go into a little bit later. So here's how to make a numeric array. Here's my list of 3 numbers. I call it numeric array, and I give it the type of the thing that I want to compress down to. Okay. This then makes a machine array where each of these is represented as a signed 8-bit integer. Okay. And this is the predicate that can be used to test that that is actually a numeric array. And then I can convert from one numeric array type to another. So this converts this integer 8 format into a real 32. floating point number. So I just specify my numeric array that I've made up here. I give it as an argument to numeric array, and I specify the target type, and I get this new numeric array with the real 32 type instead of the integer 8 type. I can unpack them, in a sense, convert them back to a list, okay, by using normal. Now, normal, what we'll try to do is it will try to make a packed array, the largest machine type, machine array type that can be used to represent it if it can. Otherwise, it will unpack it to a list, okay? And this conversion is now in parallel. So if I call it range, say with 10 to the power of 8 elements, this makes a packed array, and then I convert that to a floating point, to a set of floating point values. Then you can see that this function n on a packed array now works in parallel. So this is the time to convert that from an integer array to a floating point array. This is the serial timing, and this is the parallel timing. Okay, so I can create numeric arrays with identical values but different types. So here I create a numeric array which has an integer 8 type with the values 1, 2, 3. And here it has unsigned integer 32 type. If I use same queue, then because these types are different, these are considered to be different. If I use equal is value-based, and so equal will go through these values, even though they're different types, and compare them. Okay, so this is the two ways of distinguishing between them. So most of the stuff I'm going to talk about is going on in the Wolfram runtime library here, which is a separate component from Mathematica, but used by Mathematica. It's used in the new compiler, by the kernel, by the old compiler, when you make standalone code, library link, and in the future, possibly the front end, and maybe even the number theory library, which Charles is going to talk about tomorrow, I believe. So the good thing about this is we can use a separate code base. So the Wolfram runtime library is written in C++, modern C++, whereas the kernel is not. So we can start with a modern code base and do things much more efficiently on a smaller subset of code. So that's my memory allocator in the Wolfram runtime library is 4 times faster than malloc because it uses. I'll explain to you how it distributes memory and carves up memory and stuff like that makes it faster than malloc, which is a general allocator. Yeah. So we need to make a few changes to the system in order to make these things integrate better, and also for the compiler to have a better mapping from Mathematica to, say, native C code. So one of the things we did in version 11.3 was to change underflow and overflow of machine numbers. Machine underflow is no longer detected and trapped, so that we can use subnormal numbers from the IEEE standard. Now we've made another change where there was one single value in Mathematica, this minus 2 to the 63, that was not a machine number, whereas in C it is a machine number. Okay, so C represents signed numbers in a slightly asymmetric way. The largest machine number that can be represented is 2 to the 63 minus 1. And the smallest or largest negative number is minus 2 to the 63. This was always not allowed to be a machine number in Mathematica before. And this means if we wanted to write out data or read in data, we'd always have to check for this one specific value. But now we've made changes to allow for this value. The problem is if you do this in C, if you take this number and you negate it, you'll still get another negative number. So the negation of a negative number is negative, which kind of breaks the mathematical laws. And obviously, we don't want to do that in Mathematica. So if you negate this number in Mathematica, instead of being machine number, machine integer, it will be a big integer, okay, so that we can continue to support, sort of predicates and things like that. But it does mean that we can read and write arrays of machine numbers of specific types, integer 64, integer 32, etc., without having any additional checks of things. So that's just showing you if I negate this number, it was a machine number, but the positive version is not a machine number. So one change that we've made is to sorting. So Mathematica has always used merge sort as its basic sorting algorithm since the very beginning. Never really implemented any other thing. The reason is merge sort is a stable sort. I'll explain what that means in a minute. It has a bounded subquadratic worst case complexity. It has a linear complexity for sorted arrays. So Mathematica is infinite evaluation. So if something was sorted and we want to sort it again, then it's just linear time to scan through that instead of being n log n or whatever. And merge sort uses fewer comparisons than quick sort, which is good if we're comparing expressions. Expressions are quite big, and the ordering function that's used to sort stuff can be quite expensive. So we want to keep the number of comparisons smaller. So here's an example. Here I'm asking what the ordering is of this data, and if I use a packed array, this is what I get. So I have several ones in this thing. The one that comes first should be first in my list of ordering. That's what the stable sort means. The one that comes second should remain second, and the one that comes third remains third, and then the other two values come in here. And the same thing, identical results if I use a list instead of a packed array. And that's because packed arrays are supposed to be seamlessly integrated. You're not supposed to get a different result if you use a packed array compared to a list expression. So sorting a contiguous machine array in packed array or numeric array doesn't really have the same kind of a stability restriction that we do when we're working with a generic list. So if I'm asking for the order in which things come in, it has to be the same as a list. But if I just want to sort this data, okay, here's my example from before. It doesn't really matter if this one comes in the first position, the second position, or the third position. It's just a 1 in the machine array. So this one doesn't necessarily need to come first. It doesn't really need to be a stable sort anymore, okay, because I'm just sorting this array of data. So that means that we can now use alternative sorting methods. We use a quick sort method now, which is much more efficient for contiguous arrays because it has better data locality. And the other thing is that the parallel implementations of sorting are becoming much more widely available. So here's, yeah?
The identicality true even for floats?
Yes, because they have zero tolerance. Yeah. So here's an example. So I'll make a floating point numbers for UITI in reverse. I'll make a reverse ordered list starting from a large one down to a small one. And then I'll sort this data. So here is the new sorting function using quick sort. And here it is working in parallel. And here is the same ordering instead of sorting. This has to use merge sort because it has to match the list form. Okay, and you can see that the merge sort, this is the serial merge sort, and this is the parallel merge sort. Okay, so we've gone down from this, which is the previous version of Mathematica, down to this in the parallel version of the quick sort, which is an order of magnitude faster. So a little bit about parallelization. How does parallelization work in the runtime library? We essentially carve up a vector or this array of machine integers into blocks, okay? And these blocks are chosen according to the data locality of the cache, of the processor, and according to the cost of the operation that we're performing. Like some operations might be more expensive than others, so we want to tune this block size of how we carve this up. So here are the parallel functions that have been implemented in the runtime library. Quite a few of them. So anything that's a constructor, constant array, range, multiple part assignment, take, drop, flatten, and array reshape. Of course, NumericArray, the constructor, and two packed array. The new thing that we have a couple of weeks old now is all arithmetic now works on these NumericArrays. So I can add them, I can subtract them, I can use bit operations, I can do all sorts of things with those. So we have 78 unary operations, 21 binary, and 5 ternary that we don't yet have an interface for. They're used in linear algebra. And we also have map reduction things like total, max, min-max, max abs, etc. The other thing that we have is comparison of packed arrays or numeric arrays now works in parallel too. So things like same queue or equal, if you're comparing very large arrays of machine numbers, that works in parallel as well. So here's an example of same queue with two packed arrays which are the same, and you can see it working more efficiently in parallel. And also, this is in a sense the worst case for comparison because these are absolutely identical. If I make the first element different in one of these two, then I want to make sure that my parallel version is not much slower than my serial version, and that shows that it's within a factor of 2, the parallel version compared to the serial version. So I just want to talk a tiny bit about transposition. So Transpose has also been implemented in the runtime library now instead of the kernel, and it's actually quite a complicated problem. It's not actually part of LAPACK, the linear algebra library, and there are lots and lots of cases to consider. So I'll just look at 2 of them, out-of-place transpose and this in-place transpose. Often we want to transpose something in place because of the memory restrictions. It's a very large array, very large matrix. Like sometimes they turn up in complex fast Fourier transforms, and we don't want to make a physical copy of that object. We want to actually transpose it in place, and that's actually a much, much harder open problem to do that. So matrix transpose, if I'm prepared to make a copy for the result of the transposition, then things are pretty straightforward. The only thing that we have now is that we do this in blocks for better data locality, and then these blocks can be evaluated in parallel. So the new version of Transpose, the serial version, is about 20% faster than version 12, but it also works in parallel. You can see here, this is the time to transpose a 10,000 by 10,000 matrix. Now, when it's in place, the algorithm to work in place is slightly more complicated. It's a cycle-based algorithm. The length of the cycles of things that are moved around depends on the dimensions of the matrix. So here's an example, a 3 by 5 matrix, 5 by 3, and I'm going to transpose it here. So there are 3 cycles of values that don't move, and those are the ones that are going to be sort of on the diagonal in the result. So the element 0, 7, and 14 stay where they are in the results. They don't move around. And so the position in the result is the same as the position in the thing it started out as. And there are 2 other cycles, 1, 3, 9, 13, 11, 5. So what I need to do is I need to swap 1 and 3. 3 goes up to where 1 is. It becomes orange. And then I need to swap 1 and 9. 1 goes in the place of 9, and 9 goes in the place of 1. 9 is now in the right position. Then I need to go and swap 1 and 13. 13 goes down here. Then I need to swap these 2. And then finally, I swap those 2. And all the ones in orange are now in the right place in the transpose. And then I go through another cycle and do exactly the same thing, swap 2 and 6, and then swap 2 and 12, et cetera, et cetera, et cetera. And I end up with this. Okay? And this, if I just reshape it, just changing the dimensions, okay, this is the transposed result of the original thing that we started with. Okay? So, but you might notice one thing about this. This data movement is all over the place. I mean, these cycles, they have this kind of rather arbitrary pattern, and that's not good for data locality, and it's also impossible to parallelize. So this is a good basic algorithm, quite easy to implement, but not good for data locality for large matrices, and not good for parallelization. Elegant, simple to implement, doesn't use the cache efficiently, and it's inherently sequential. So we've implemented a new algorithm which does work in parallel and does have data locality. So it's a recent paper from 4 years ago. There's only 2 implementations I'm aware of. And the idea is to consider this matrix as a 2D array instead of a 1D array. So before we had these cycles that worked in 1 dimension. Okay? But now we do operations that work in 2 dimensions. So here's my example of a 4 by 8 matrix. the GCD of 8 and 4 is 2. So the first thing I'm going to do, because the GCD is not 1, is I'm going to need to do like a pre-processing step. That's this column rotation. And I'm going to move things around in columns in blocks of 2. So 24, 28 that was here is going to go down here. And 16 and 20 is going to go here. 8 and 12 is going to go here. Then once I've done that, and this is only done when the GCD is not 1, then I'm going to shuffle stuff within each row. Okay, so 7 that was here goes to the end, 3 that was here goes here, etc., etc. So I'm ordering stuff within each row. And then once I've done that, I'm going to order stuff within each column. So here and here, and here and here, and here and here. So what you can see about this, it has very good data locality, because all the operations are working only on single rows and on single columns. And also, they're working in a completely independent fashion, so they can be parallelized. I had a timing chart here that I didn't put in anyway. Anyway, so then we've made some other optimizations to this arithmetic, to this in-place transposition that got us a factor of 4 speed up. Essentially, we don't want it. The algorithm involves expensive modular arithmetic on every single index computation. We don't want to do that. Modular division, etc., is quite expensive, like division of integers on a CPU. So we make use of the fact that we're working on a grid, and we do only one expensive computation and just move to the neighbors using a cheaper arithmetic system. Okay, so we've worked that out in Mathematica. And we've managed to get this algorithm to work 4 times faster than was previously implemented. So now we're within a factor of 2 of the out-of-place transposition, which is about as good as things can get. So lastly, with the time I've got left, I'd like to talk about arithmetic, since I worked so hard to squeeze it into this talk. So I think Todd Gailey yesterday said, this isn't available generally, it's only in his version, so this is only in my version, and is completely a work in progress. Now, the arithmetic is fully implemented in the runtime library. The question is, how do we expose it to the user? Okay? And we have several choices, and I'll try and explain to you a little bit about what those choices are and why we're leaning one way instead of another. But just to show you that it works here, what I've done is I've made a vector of floating point numbers. This is double precision. It's a packed array here. And I've gone and evaluated the square root function both in serial and in parallel. Then I've now made an array of floating point numbers. So I've taken this array of double precision numbers, and I've used the NumericArray to compact them down to 32-bit floats instead of 64-bit floats. So they're single precision instead of double precision. And you can see that the memory is cut by half. And this is a comparison of the timing to evaluate the square root function. And you can see in serial, it's about 2.5 times as fast. In parallel, it's about twice as fast. So working with single precision numbers, with square roots, if I'm not so interested in the accuracy of something, I can compact it down to a float. I get a factor of 2 gain in memory and a factor of 2 gain in speed. So what's the problem? The problem is when we have mixed types and we're using binary operations, say we want to do plus, but we're doing plus of an unsigned integer 8 and an integer 8. So the types aren't compatible. Okay. If we start to do that, allowing that kind of thing, then we're going to have a proliferation of the number of routines that we have. We have 12 types. If we allow each cross of those types in binary arithmetic, we're going to have 144 cases of plus, times, divide, etc. Then if we allow that for ternary, it's going to be 1,000 odd routines every single time. So I actually tried that in the runtime library, allowed every cross type, and the compiler crashed. It wasn't even able to compile the thing. It ran out of memory and crashed, and I had 32 gigabytes. And also, when I did get it to succeed on a bigger machine, the runtime library binary became bigger than the kernel binary, which is not really the sort of thing that we want. So we really have to make some choices and restrictions about the sort of thing that we want to do here. So do we really want to support the arithmetic in the kernel? This is the question. So here are a couple of examples comparing the kernel arithmetic to the compiler arithmetic. So if I take a numeric array that has a definite type, and I use part in it inside the kernel, where the only thing the kernel can do is make what it knows as an integer out of that thing. We don't have a representation of typed numbers in the kernel. So I've lost this information. I'm taking out this 1 here, but this 1 was an integer 8 type. I've extracted it from a vector, and I've made this scalar 1, which is a machine integer. Okay, just 2 minutes, and then I'll round up. Yeah, so which is a machine integer. So I've lost this type information. Okay, so that's a problem with doing things in Mathematica. Or we introduce type numbers. For every single type, we have a 1 that's an integer 8 type, a 1 that's an integer 16 type, and we have a proliferation of things. Or we do it through the compiler. Because the compiler already has a type system, it already knows about numbers of different types. And it already knows about a lot of the infrastructure that we're going to need to do those kinds of things. Here's another example. I have 2 numeric arrays, and I want to subtract them. So I write NA1. They're both unsigned integer 8s. But the kernel converts a subtraction into plus of the first vector minus the second vector. It converts this into a plus and a minus. And minus of an unsigned integer type is not a good thing. We'd have to use some kind of, we'd have to decide is that an error or not, or is that allowed? We're allowed to do the 1's complement or whatever of the unsigned representation. Whereas in the compiler, we can do that subtraction directly without any of these problems. And similar kinds of things, if I want to do an expression that's 1 plus 2 times na to the power of 2, these are all machine integer 2s or machine integer numbers. Whereas in the compiler, I can mark these up as a definite type that matches this. So this is a way to do that. Say that I have an expression if x is less than 0, I can type mark up this 0 to be the same type as the original input. And so everything in this computation matches this type of the inputs, and I'm working in a fixed type domain there. Yeah, so what would it look like? So we haven't hooked this up yet, but what would it look like? So this is the compiler's specification when it works with a vector packed array of this type. So it would look like this, exactly the same. This is packed array. This now becomes numeric array, except we're allowed to use different types in order to do the arithmetic. So in order to avoid, at least in the first version, or several versions, however many it's going to be, all of these complicated problems in the kernel exposing all the arithmetic on these numeric arrays, the first thing that we'll do is have them to work through the compiler, where it's a much more uniform sort of environment. So just to conclude, NumericArray is an extension of packed array, and it includes more native machine arithmetic types. The packed array data structure is actually been unified with the NumericArray data structures. They all use exactly the same code now. So we've eliminated the packed array code and made it a subset of the NumericArray code. Then we can focus on optimizing just one implementation. All the arithmetic and the structural operations are performed in Wolfram RTL. So some of them are being moved there from the kernel, and some of them are being rewritten inside the RTL. We use OpenMP for parallelization. If you're just a casual user of packed arrays and you don't care anything about the compiler or anything else, or NumericArray or anything else, because they're now the same code base, everything that you've done before that uses packed arrays will now work faster, irrespective of everything else. So as I said before, the reason to do this in a separate library that's linked into Mathematica is because we can use a more modern code base. So this is just a bit of history of the Wolfram RTL library. This is when we started working on packed arrays and then exported this library for external C code. And then this is when we started working on the new compiler, and you can see sort of the development that's gone on, and this is the number of files that we've sort of been adding over time. And the code base is growing, but it's not growing too much, because as we go and remove lots of C code, often the C++ code is much more compact. So I've written something like 250,000 lines of code, but I've removed 200,000. So yeah, that's pretty much, sorry, that's everything. Thank you very much.